Welcome to our last section on algorithms, the last missing piece, and that is dynamic programming. Sounds very important, doesn't it? With this section, we're going to go over the very last piece of our mind map to complete our entire knowledge graph, so we're ready for interviews. It's this last little piece of dynamic programming, specifically memorization, that we're going to be talking about. But what is it? Dynamic programming is just an optimization technique. And here's the fun fact. Dynamic programming actually means nothing. It's completely garbage buzzword. And I'm not kidding here. I'll link to a funny article on how the name came to be. But dynamic programming, at the end of the day, is just an optimization technique using something called caching. If you have something that you can cache, well, then you can use dynamic programming. Now, we're going to get into the details of what that means throughout the next videos. But at a high level, dynamic programming is a way to solve problems by breaking it down into a collection of subproblems, solving each of those subproblems just once, and storing their solutions in case next time the same subproblem occurs. But let's get into that and understand what it means, how we can implement it to become better interviewers, better engineers, and better programmers. I'll see you in the next video. Bye-bye. In order to understand how dynamic programming works, we need to understand what caching means. Caching is a way to store values so you can use them later on. Ideally, you can think of caching as a backpack that you take to school. Instead of going all the way home when you need something like a pencil, you have a small box on your back that holds items that you need so that when you go to school, you can just reuse them fast over and over. Now, that's a bit of a silly example. Caching is just a way for us to speed up programs and hold some piece of data in an easily accessible box. And memorization is a specific form of caching that we're going to be talking about because we use it a lot in dynamic programming. But instead of just talking about it, let's actually demonstrate it in code. The way we can cache things, well, let's imagine we have a function that says we want to add to 80. And this function takes a number, and all it does is return the value of n, that is the parameter we give it, and adds 80 to it. So that when we run the function add to 80, and let's say we put in 5, we get 85. Nice and simple, right? But if I run this function again, I'll have to go through this step again and add 80 to that answer. And if I do this again, do the same thing. I've ran the calculation 3 times. But what if this operation took a really, really long time? What if I had a console log here and we can imagine that this operation takes multiple seconds? It takes a long time. Every time we run this function, we'll have to run long time 3 times and go through the step one by one, even though we've done the exact same calculation 3 times. Is there a way that we can optimize this? And this is where we can use caching and memorization. Let's improve the above function by doing something different. I'm going to create a new object called cache that's going to hold an empty object. We're also going to have a function that is now going to be called memoized, add to 80. That takes a number. And inside here, we're going to do something a little bit different than the above. We're still going to add to 80, but we're going to do it in a special way. I'm going to say that if n is in cache, and this is a way to check if a property exists in an object in JavaScript. So it's similar to me doing cache.n to check for the property. This one just reads better, so I'm going to keep it like that. So if n exists in cache, so if we've cached it before, then simply return the cache.n or cache n. So return the cached value. But obviously it's empty the first time around, so this is not going to work. If there's nothing in the cache, which is the case the first time around, well, we have an else statement. And in here, we're going to have our cache n, which doesn't exist yet, and assign it n plus 80. So that after this, if we do something like memoized add to 85, it's going to say 5 plus 80. So in here, we're going to cache the property 5 to have a value of 85, which is what we're doing here. So that the next time around, we're doing something like this. We go through the if statement, find the fact that we've already calculated 5, and just do simple property access, which, as we know, is all of one time, is super fast with a hash table like this. Let's complete this example to show you how it works. I'm just simply going to return cache n, since we just filled it up here. And let's just have a console log here that does long time to see that we're doing the calculation that takes a long time. The first time I run this function, I get 85, and oops, I have the cache pre-filled, so it didn't calculate the long time. Let's try that again. Click run, long time. The first pass through, it went through here and did this calculation that hypothetically is going to take a really long time. Again, we're using a nice, easy example here, but you can imagine this being a calculation that takes a long time, many seconds. What if we do this again? We can console.log here to make sure that we capture these values. And we'll label them 1 and 2, just so we can distinguish them. So the first call and the second call. If I hit run, look at that. First time around, we call long time and we calculate to 85. But the second time around, because this value was in the cache, we didn't have to do this long calculation and we just returned it immediately. So what is memoization exactly? Well, memoization is a specific form of caching that involves caching the return value of a function, that is, the return value of this function, based on its parameters. And if the parameter of this function doesn't change, like it is here, then it's memoized. That is, it uses the cache because it's calculated the same thing before with the same parameter, and it will return a cached version of the function. It's memoized. If the parameter changes, well, it's a different parameter that it's never seen before, so it's going to calculate both times. Different things. And I just noticed here that this shouldn't be 5, it should be n over here, so it's dynamic. There you go, that's better. So remember this. Memoization is simply a way to remember a solution to a solved problem, so you don't have to calculate it again. Welcome back. I want to improve this function just a little bit. You see, ideally, we don't want to fill the cache in what we call the global scope. That is, to be living outside of this function. Ideally, it's good practice to have memory, or in this case, the cache, to live inside of this function, not polluting the global scope. And there's many ways to do this based on the language. In JavaScript, we can use something called closures. And this is what it would look like. And I'm showing you this because when we get to dynamic programming, you're going to see this pattern a lot. Luckily, with dynamic programming, the pattern is usually always the same. So once you learn this, then it becomes easier and easier. So the way we bring this inside of the function is to, well, bring it in like that. But the problem is now that every time we run this, we get long time each time because the cache gets reset every time the function gets called. So the cache becomes an empty object. To get around this, we can use closures in JavaScript. And we can return another function, so a function that returns another function. And in here, we'll pass the parameter n. And we'll have the logic inside of this function. That's it. And because of something called closure, we're able to access this cache inside of this child function. Now, this isn't a course about JavaScript, so you can read up on closure on your own. But this is just a way for us to avoid that global scope. So that this time around, we can do something like this. We can simply say const memoized equals memoized add to 80, and we'll run this function. And we can actually even remove the parameter from here so that we have flexibility. Let me show you. We have the memoized here, which hopefully I can spell, memoized, so that now this function, because I ran it, is going to return for me this function. Memoized equals this function. That's literally what memoized add to 80 returns. And I have access to this cache variable. So that in here, I can just say memoized 5 and memoized 6. If I hit run, I still get the same thing. But if I do 5 and 5 and I hit run, look at that. It's memoized. This function remembers that the parameter has not changed. It's the same parameter, and it's going to check the cache and say, I don't need to do all that silly calculation. I already have it. Here you go, just using a hash table. Here it is. And what we just learned here is really powerful because it allows us to be very efficient with our code, something that we know interviewers love, companies love. And dynamic programming allows us to use what we know now about memoization to optimize our code. Let's find out more in the next video. Welcome back. I want to show you one last example. And this is probably the best example of why dynamic programming is so important. And as you remember, when I say dynamic programming, which sounds kind of confusing, just think of caching, of optimizing something using a cache. One of the best examples of why dynamic programming is so good is our good old friend Fibonacci sequence. We learned about this in our recursion section of the course, where the previous two numbers add up to the next number. So that 13 is 5 plus 8, 34 is 13 plus 21, and it keeps growing, keeps growing, keeps growing. And we learned how to calculate that, right? We were able to calculate the Fibonacci number quite easily. We had function Fibonacci, which is a really hard name to spell. I believe it's this way. And all we did was we said, using recursion, we had a base case of n is less than 2. In that case, we'll return n. Otherwise, we did some fun recursion. We return Fibonacci n minus 1 plus Fibonacci n minus 2. So that if I want to find the Fibonacci number at index of, let's say, 6, and I run this, and this should be n as a number. Let's run that again. I get 8 because 0, 1, 2, 3, 4, 5, 6 is 8. If I do 7, I should get 13. Awesome. This is something that we should be familiar with. But let me ask you a question. How efficient is this function? And we've talked about it before, right? It's not very efficient. If I have a variable here that says, let's call it calculations, which will equal to 0, and we're just going to increment this every time this function gets called. And because it's recursive, we know that it gets called a lot of times. If I do Fibonacci 7, how many calculations is that? That's 13 calculations. So 13 times that we ran through the Fibonacci function. What if I increase that to 8? 21. Okay, what about 9? 34. What about 10? 55. All right, it's increasing pretty fast. What if I do 12? 144 calculations just to get the 12th index. Wow. What if I do 15? 610 calculations. What about 20? Holy moly, over 6,000 calculations. And just for fun, what if I do 25? Oh boy. All right, one last time just because we're having fun. 30. All right, that's a lot of calculations. And by the way, if you want your browser to crash, just type in 50 or 60 and see what happens there. Regardless, if we look at this, well, is pretty terrible. Just to calculate the 30th number or index of a Fibonacci sequence takes that many steps, that many calculations. That is a lot. It's not very efficient. And we know this, right? Because in our recursion section, we talked about how that Fibonacci sequence and the way we're running the function is O of 2 to the power of n. Really, really bad time complexity. As we saw, just doing 30 calculations takes a lot of steps. And remember, with recursion, we're adding every nested function call adds to the stack, which increases our memory complexity. And we would never want to do an operation that costs this much in real life. So how can we make it more efficient? Can we make it more efficient? I mean, if you wrote that function, is your boss going to fire you because it scales so horribly? I mean, if your boss is horrible, maybe. But if you know dynamic programming, you can avoid this. Because what if I told you that we can do O of n with this function? Because with dynamic programming, we can. That's right. We can go from O of 2 to the power of n all the way down to O of n. Sounds like magic, doesn't it? And this is where we get to the next step of our dynamic programming. We can reduce the time and space complexity of our algorithm by using memoization. And we can do this because the solution to each subproblem is what we call optimal. That means we do a lot of problems repeatedly that are the same. In the next video, we're going to explain this concept and see how we can use memoization. I'll see you in that one. Bye-bye. Welcome back. If we take a look at our Fibonacci function that we created, this is what we're doing. If I was looking for a Fibonacci number of 7 using recursion, well, we'd have to run all these calculations recursively and all of these as well. And you can see here what's happening, right? Look where we're calculating Fibonacci of 1. We have this function running 1, 2, 3, 4, 5 times, calculating the same thing. What about Fibonacci of 2? Again, look at all these calculations that are being repeated. What about 3? And you see here where the triangles are overlapping, where we're calculating 3 over where we calculated Fib 2 and Fibonacci of 1 as well. And then if we keep going to Fibonacci number of 4, there again, repeated tasks. Triangles over triangles. And then finally, Fibonacci of 6 or 5, we see that once again, we just have more repeated calculations. This does not look efficient, does it? And that's what we saw in the previous video. This is what we're doing with our calculations. But if you notice here, with dynamic programming, we can optimize this and use memoization to say, hey, calculate Fibonacci of 7, go recursively down to 6, to 5, to 4, to 3, to 2, and also to 1. And now, as we go back, remember, as we start to return the statements, and we go to Fib of 2, or Fib of 3, or Fib of 4, because we've already calculated these numbers, we can actually return a memoized version so that all these calculations are no longer needed. Why? Because 2, 3, 4, and 5, every time we ask for it, in this case, we've already calculated on the left-hand side. So we can use the cached or memoized version so that these we can just ask the memoized function to just give for us. We avoid all these calculations. Look how simple that looks. And I'm going to show you in the next video how we actually implement this with the Fibonacci sequence. But to demonstrate to you that this is not only just this problem that we can use dynamic programming on, I have a set of rules. One is that you can think of dynamic programming as combining divide and conquer, what we did with the tree-like structure of Fibonacci number, where we use recursion, and using reuse, that is caching and memoization, with recursion to get savings in performance and use dynamic programming. And these are the steps that I like to follow to see if a problem can use dynamic programming to optimize it. We first ask, can the problem be divided into subproblems? That is it a tree-like structure where each problem is broken down into smaller problems, into smaller problems, into smaller problems, which usually indicates a recursive solution? Again, something that we're very familiar with from our previous videos. And now the third question is really important because you can have tree-like structures that don't have repetitive subproblems. But if these subproblems are repetitive, that is, we're doing the same calculation over and over in these subproblems, well, if the answer is yes, then we can memoize these subproblems. And once we do that, we see tremendous benefits. And these benefits are used all over computer science to improve performance. So that the fifth step should be to demand a raise from your boss if you've implemented this because you've just saved so many calculations, so much time complexity. I want you to think like this. Instead of being intimidated by the confusing name that is dynamic programming, You just need to know when a problem can use this technique. And I'll leave some problems for you after this section to practice on. But you want to just follow this pattern. When a problem has solutions composed of solutions to the same problem with smaller and smaller inputs, each subproblem is solved only once, and the result of each subproblem is stored in a table like a cache, such as a hash table, like we've done in the previous video, for future reference. We can use this table to obtain the original solution of a repeated problem. Enough talk. I think it's time for us to implement our own memoization with Fibonacci number. If you want to challenge yourself, go ahead and see if you can code it yourself. Otherwise, in the next video, I'm going to show you how to improve our terrible performing Fibonacci function into O of n. I'll see you in that one. Bye-bye. Welcome back. Let's use dynamic programming and memoization to improve this function. Just like we did when we learned about memoization, this is fairly simple. Let's remove this for now. I'll keep this at the top. And in here, create a new function. We'll call it Fibonacci master. This function will have a cache, a hash table, or an object to store our pre-calculated answers. And if you remember, because we want to make sure that we don't reset this every time we run this function, we're going to return another function inside here, again, using closures in JavaScript. And in other languages, you might have to use different techniques. And in here, we can just have a function. We can name it whatever. Let's call it fib. That takes n. That is the number we give it. And inside here, well, we do something very similar to the above, except we're going to check the cache first. We're going to say if n is in cache, just like we did in the memoization videos. And we're going to check if the cache exists. And if it does, we're going to return cache n. The first time around, this is going to be empty, so it's not going to work. It's going to go into the else condition. And in here, we have two conditions, just like we do up here. If n is less than 2, then we need to return n, just like we did above over here. Otherwise, we run our sequence. So we do fib of n minus 1 plus fib of n minus 2. But we want to store this value in our cache. So we're going to say cache n is going to equal the result of this. And finally, we want to return this value because we are using recursion here, and return cache of n, which we've just set. And that's it. That wasn't that hard, right? I mean, we have a few extra steps, but all we did was just add the result to our hash table. So that now, if I do const, let's say faster fib is going to equal to Fibonacci master. Remember the first time around, we're going to run this function and create the cache variable. Whoops, let's try that again. And create the cache variable, and it's going to just return this function. So it's similar to just saying like that, faster fib equals this function now. Except that now we have access to the cache variable. So that now I can console.log, and let's call this DP for dynamic programming, and we'll say faster fib and give it, let's say, 10. If I run this, I get 55. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 55. That's pretty good. But let's do something fun here to see if it works. This calculations tally that we used in Fibonacci number, let's move it to the Fibonacci master. Or instead of here, down in this function, because this is the one that we were recursing over. And let's see how many times this calculation happens. If I run this, oh, and we need to console log these calculations. So at the bottom over here, let's have a console.log. And we'll say we did calculations, just like that. So that if I run this, we see that we did 19 calculations with the Fibonacci master when we entered 10. Versus if we move back calculations up to here, to our old version, oh, and we actually have to run this function. So in here, let's just have console log so we can have everything clean. We'll say console.log. This will be called slow, and it will be called, what was it? Fibonacci. So we'll just do our original function, Fibonacci, with 10. So let's see and run. We got the same answers, 55, but it took us 177 calculations to get to 10. Holy moly. So 19 versus 177 calculations. And if we do 20 here, well, we have that many calculations. And actually, let's just do 35. See if that's possible. Let's see 35. There you go. Look how many calculations we had to do. Versus if I do 35 with our memoized function, move the calculations in here. And we run this. 69 calculations. That's it. Instead of before, where if I entered Fibonacci 50 here, it would actually crash the browser because we would do so many calculations. With this one, I can do Fibonacci 100. And I have no problem. Look how fast it calculated that. That's pretty amazing. It only did 199 calculations. I hope you see the power of dynamic programming. And it's not that hard, right? All you need is to remember this pattern. And if there's any repeated calculation, to just memoize the result of a function. So that if the parameter is the same, we check in the cache first for the result. But let's talk about space and time complexity here. This, well, because we're only doing the necessary calculation, in this case, all our calculations, well, are n, right? We do 1, 2, 3, 4, 5, 6, 7 calculations versus all the ones that we did before. So that our time complexity for this one is O of n. Versus with this one, that was O of 2 to the power of n. Just like that, we made huge savings. The one drawback is that, well, we increased the space complexity, right? I mean, with the first Fibonacci number, we had to add functions to the stack. And these functions, the deeper it is, we added to the stack. But once we got to the bottom, we popped off the stack so that the stack was as deep as the tree. But with the memoized version, we also have this new variable, this cache hash table that we have to store our memory in. But as we know, we sometimes need to trade off space complexity for better time complexity. And this is what we're doing in this case. And in this case, the time complexity savings are very large. All right, I hope I got you excited about dynamic programming. It's very interesting and not as overwhelming as you think, right? I'll leave a couple of problems for you to do to get used to dynamic programming, but I recommend that you take the code that I'll leave here for you and you can just grab it from resources and play around with it. Otherwise, I'll see you in the next video. Bye-bye. Welcome back. In this section, we finalized our understanding of algorithms with dynamic programming. And we've completed all of this. And now, the very last piece of the puzzle is complete. Dynamic programming, and specifically using memoization to optimize our problems, completes our entire diagram, our mind map of how to master the interview. So what did we learn? We learned that with dynamic programming, we can identify these types of problems by first seeing, hey, is there a problem that can be divided into subproblems of smaller pieces, where most likely you're using recursion. If you're using recursion, then ask yourself, are there any repetitive subproblems or tasks that I'm doing over and over? In that case, we can memoize these subproblems so we don't constantly recalculate things and use this idea of dynamic programming so that we get a nice raise from our boss because we just made the code so efficient. Now, memoization is a common strategy for dynamic programming problems, which are problems that I just described here, such as the Fibonacci problem. There is one other way of incorporating dynamic programming, and it's called bottom-up approach. And we won't focus too much on it, but I want to show you quickly how it might look like. In our case, there's actually a third way to solve this problem. And the way to do it is, well, it's actually fairly simple. We can do Fibonacci master 2. And in this function, we'll have the answer, which will be the list of our Fibonacci sequence, which is right up here. And we're going to pre-fill it with 0 and 1. And then from there, all we do is a for loop and say, let I equal to 2, because we're now starting at the second index. I is less than or equal to the number n. And we'll increment I. And then finally, we will say answer.push. And we'll push to the next item in this stack the results of the first and the second. So I minus 2 plus answer I minus 1. And then we can just return answer dot pop, which will give us the very last item in the list according to what index we're looking for. So that if I run this and call it dp2, I should still get, oh, and I have to make sure that I pass in, let's say 100. If I run this, there you go, we get both of the same results. And this type of approach avoids recursion. Some would say is not as clean, not as easy to understand, while others will say, no, this makes a lot more sense. It really depends on your preference. And this type of solution is called bottom-up because you start from the simplest solution from the bottom and slowly work your way up higher and higher towards more complex problems. But these types of problems, although easier to see, are harder to figure out when to use. So I prefer the top-down memoization approach of using this. But I just want to show you that there is another way of doing things. And in an interview, it's very rare that you're going to be asked to implement both methods. But at the end of it all, I hope you see the power of dynamic programming, this simple concept of saving ourselves a lot of trouble thinking about how our programs run and how we can optimize it so that we don't do any repeated tasks.